Welcome. This is the presentation of our ICCV 2023 paper titled Efficient Controllable Multitask Architectures. Multitask learning, where multiple predictions are made for a given input, provides several benefits over individual single-task architectures, like decreased inference time, increased sample efficiency, and better learned representations. It is not always easy to train all the tasks to achieve good performance simultaneously, especially when the number of tasks increases. Further, users may have varying requirements for model usage based on task preferences and available compute. Not all preferences require complete model capacity. This leads to a challenging but interesting problem of creating a dynamic approach where the multitask model can adapt to diverse scenarios based on task preferences and compute budget. To understand this, let us consider a surveillance scenario where we have a multitask model which performs pose estimation, activity recognition, and identification. At a certain point of time, the user might require high performance only in identification, but some moments later, we might not care about it all, rather focusing on the other tasks. Similarly, the user's compute budget can also change dynamically depending on the device of deployment. These practical requirements motivate the problem addressed in our paper, where we aim to dynamically adapt multitask models to these changing task preferences and compute budget. To formalize, we aim to train a single multitask model which can adapt its architecture given any task preference and resource constraints during inference, without retraining. To make this more explicit, let us again take the example of two tasks. In a conventional multitask learning setup, a single model will be learned with respect to a predefined task trade-off. In contrast, we introduce a method for task trade-off, which allows us to learn the entire trade-off curve. Our method incorporates the resource budget, which allows us to learn a family of trade-off curves. This gives us key advantages over conventional approaches in terms of scalability and flexibility. Prior state-of-the-art methods proposed a method to base their parent architecture using single-stream models. However, this becomes inhibiting when the number of tasks increases. Further, this method did not allow precise sample target architectures that followed the resource budget. In contrast, our proposed method ECMT shares a common backbone across all tasks to address scalability and can sample target architectures that strictly follow users' budgets. ECMT prescribes a two-stage method to sample the target architecture. Stage 1 involves training the parent architecture composed of slimmable convolutional layers. Stage 2 involves searching for the target architecture sampled using the joint task and compute preferences of the user. Let us expand on these steps. During training, we create a multitask model composed of slimmable convolutional layers in both the encoder and the decoder. Slimmable layers allow us to define and control this parent architecture by setting the width ratio or number of filters for each layer. Our training method involves a novel knowledge distillation loss that distills the features of the parent encoder to the child encoders. During inference, we use the task preference to set the width ratio of the decoders, where a higher preference for a task results in a higher width ratio for this task's decoder. Then we search for the optimal encoder layer widths that extracts the best overall performance while satisfying the compute budget. With this novel strategy, ECMT can precisely control the parent model for optimal resource allocation for diverse scenarios. In summary, we develop an efficient multitask model which can adapt its layer-wise filters during inference given any task preference and resource constraints without retraining. Please visit us at our poster session. Thank you.